I'm José Ángel Bejarano Vázquez. I am a PhD student at the National Metallurgical Center in Madrid, Spain. And this is the project that I've been working on for the past year. It's about building a package for with FEniCS for simulating laser powder bed fusion, which is a procedure of additive manufacturing for metals. So go ahead with the motivation.
It doesn't work, I'm afraid.
It doesn't. Ah, okay. Yeah. Sorry. So first of all, to make sure we are on the same page, I will give a very brief explanation of what is laser powder bed fusion. It's a procedure of additive manufacturing. Additive manufacturing is 3D printing, but with metals. And specifically, laser powder bed fusion is a procedure where we display a layer of metallic powder, let's say stainless steel, maybe alloy of titanium. And this is a very thin layer, like 30 microns or so. And then we display, we put a high energy laser over it, making a path. The metallic powder will melt, and we will have our first layer, and then we can keep on building more layers and more layers. This is a really, this procedure is really good for making some specific pieces, but it also has its flaws. Mainly the defects that are formed on the microstructure of the pieces, like such as pores, lack of fusion. These kind of defects really compromise the mechanical properties of the piece, and we cannot afford that. And the biggest problem about this is that nowadays the most common way to attack this problem is by trial and error, and trial and error is really expensive. So what we do is that we do trial and error on simulations, which are less expensive than on real experiments, but still simulations are really slow. This is a really complex procedure, and simulations of a big piece can take up to hours of simulation. So my motivation was using machine learning to predict the temperature profiles of these pieces, but for that I needed a database, and I had to make my own database out of finite element simulation, and thus using FEniCS, since it could be really well integrated in my Python workflow. So about my model, it's really simple. It's just considering heat conduction. This is a very complex procedure, and there is several physical phenomena involved, such as melt pool fluid dynamics. The melt pool is the part that is melt in the around the laser. But computing those fluid dynamics will be too much and really computationally expensive. So if I want to build a whole database out of this, I have to skip that part and make some considerations around it. So yeah, actually the FEniCS implementation of this problem is quite simple. It's heat conduction on a steady mesh, but what is more challenging is how we can approximate this problem, and thus for example, how can we approximate the laser? I did it via this heat source, which is a Gaussian heat source, but it has a negative exponential term on the vertical axis, so we can simulate that porosity of the metallic powder and how the energy can go inside. But yeah, the FEniCS implementation is quite straightforward. It's important to take into account the properties of the material. Conductivity, thermal heat capacity, and density are really important, and they depend on the temperature. So I have two different functions for it. One for the powder that has a very specific properties, because it has pores and the conductivity is way less and that stuff. And yeah, the model distinguishes between powder and not powder, and when it melts, it becomes bulk again. And yeah, this is the implementation. I did some validation, experimental validation with the information of an article that I found out, and the validation is quite good. But yeah, we can see some flaws, specifically on the depth. As we put more energy input on the simulation, the real depth is higher. This is because of this is the major flaw of not using melt pool fluid dynamics, because this is called a keyhole effect, and is about a pressure that is making the surface of the liquid towards the depth, and thus the model simplifies it too much. But besides from that, those are errors that we can afford, especially if I'm looking for thermal profiles, because we can see high errors sometimes, but the difference in Kelvin in that area are not that big. It's just that they are above or below the thermal point, the melting point. But since what I want to predict are the thermal profiles, this is good enough. This is an example of a really simple thermal simulation. So we can see the melt pool and how the laser is going. This is a continuous laser. This package that I made has a lot of options. Can be a pulsed laser. We can change a lot of printing parameters, and we can simulate different layers. And finally, I did once I got it built, I did a dataset generation out of it. This is important, but there are plenty of printing parameters that are interesting, but I was especially interested on the path that the laser follows. There are a few industry accepted scanning strategies, but I wanted a machine learning model that can predict any single scanning strategy, and for that I had to build a database out of random paths. They are not literally random, because it's not about dropping some random points and then linking them. It's about dropping random points and then linking them with segments of other laser incidences, because this was with a pulsed laser. But I need to do this in order to break the bias that the neural network was making if I only consider industrial scanning strategies. But with this, and also 3 different laser powers, which is the most important printing parameter when it comes to the heat treatment of the piece, it was enough to get a good model, and these are the machine learning results. Honestly, this is really ambitious work, because I want to predict any thermal profile across the whole piece for any scanning strategy. But yeah, for the test set, I used some scanning strategies that are accepted on the industry, such as the zigzag, the spiral, and those that are a little bit more funky. But yeah, it went pretty well. I mean, there's room for improvement, but this is in procedure of publication of a job. It was accepted, and yeah, I wanted to share the package when I came here, but I'm doing still the paperwork with my institution, so I can publish it online. So if anyone wants any information, he can contact with me, and I can arrange that. So yeah, this was everything.
Questions?
Yeah, thanks a lot. Could you elaborate a little bit on you optimize the strategies, but with respect to what? To minimize distortions, to avoid inclusions, force?
I didn't optimize. What do you mean by optimizing? What do you say about that?
With your ML model, you're looking for
No, no, I'm just looking for predicting thermal profiles.
Thermal profile.
Yeah, those are the thermal profiles, and what I'm predicting. The input of my model is the printing parameters, which right now is only laser power and the scanning strategy, the path of the laser. And with that input, well, the path of the laser relative to the point that I'm studying, and I'm predicting the thermal profile. And with that input, my model predicts the thermal profile.
Can we say that you computed a lot of cases, and with your ML model, you interpolate between those results?
Yeah, that was my intention, making the database with random scanning strategies. So my model could break the bias and finally predict a really broad number of cases, because if at first the first time that I tried this, I only took into consideration a couple of these scanning strategies, but when I asked the model for the thermal profile with another scanning strategy, it didn't work. So I had to build a, let's say, random database with my package so I could get this model working.
Yeah. Can you comment on the influence of your polycrystal structure on the heat conduction? You have a polycrystal, right?
I don't. What do you mean? In the
from the powder, you
Yes.
melt it up, and then the way it crystallizes. And you said it's a stainless steel.
Okay.
It probably means you have a polycrystal structure in the end.
Yeah, this is. I didn't work on that yet. This is why I'm predicting thermal profiles. So with this information, I can use other software to predict the structure and the phases of the material, because
the grain structure probably influences your thermal conduction in the material.
Yes.
Thermal profile.
Yeah, but the conduction of the material is. I took it from the literature for similar problems. Yeah.
Yeah.
Very nice talk, thank you very much. What I'm wondering, I think you treated the entire block with homogeneous heat capacities and homogeneous conductivities, is that correct?
No. Well, I don't have a proper image, but there is a, well, we can kind of see it here. Like, this is the layer of powder, and it has different properties, which are taken from the literature. For powder, this example is with stainless steel 316L, which is commonly used, so there's plenty literature. So these are the experimentally measured properties of that powder. And then this is the properties of the bulk material. And once it melts and it heats down again and it solidifies, I use the bulk properties. And those are, all of them are depending on the temperature. Yeah.
Is there volume change involved? Because if you
No.
have powder, okay, but would in reality, is there volume change? I would expect some kind of a shrinkage because you have empty spaces between the particles. And
Yes, I think so, and also there are more complex phenomena such as splattering and veiling, which because of the high energy, some pieces of powder go straight out. So yeah, it's really complex.
Okay, thanks, the speaker.